The importance of power usage in networking devices cannot be overstated, whether you are concerned about your carbon footprint or just your electricity bill. And today we will try to identify what consumes energy in Juniper routers. There are actually multiple initiatives related to power and energy in the company at the moment. To name a few, I'll start with the chassis power management. That's how we manage the energy budget in a modular system. Based on this budget, we can decide if we have enough to boot up a line card and what should be the order of priority. There is also the Power Characterization Initiative, consisting in defining a common and consistent test methodology to measure energy across all the products in our portfolio. We started some initiatives around monitoring and observability. The purpose is to display as much energy-related information as possible through CLI. That also includes the creation of native data models to expose all these counters. Then we have the power optimization features at the router side or the network level. In the second case, that implies protocols and potentially controllers. But that's the first category here, the device power optimization, that will be the interest of these videos. And it's just common sense. What can we shut down and what can we slow down to reduce the energy consumption, still maintaining an appropriate level of services? And before going there, we'll need to understand what consumes power and what are the parameters influencing this consumption in the different parts of our router. That will be the scope of the first video. The features and improvements that we are bringing are in the second, and I will put the link in the description below. Let's start with an example. It's a PTX 10001 36MR, a 1RU router made of 3 packet forwarding engines connected through a fabric ASIC. Since it offers a mix of 100 GigE and 400 GigE, certain ports are connected to a PHY, an Ethernet transceiver component between the optical cage and the PFE. That increases the fan-out, the port density if you want. We noticed that at 20C, the top 2 power consumers are the PFEs and the optics. And in this case, the optics are just FR and LR, not even ZR, ZR+. You can easily imagine that in the future generation, 800 GigE or 1.6T with high power optics, that will require more energy than any other component in your box. So the second example I'm picking to introduce a discussion is another PTX. That's a modular chassis this time with 8 line cards, LC1201, fully populated with 400 GigE LR8 optics. That's 36 pluggable per slot. If you compare 30% traffic rate and 25C to line rate and 40C, you will still find that the PFE in the line cards are the top consumers, and the optics are second. But the fabric cards in the chassis are consuming significantly more than a single ZF chipset in a pizza box. We note that the fan will consume twice more energy in the second case. Let's keep this modular chassis example to illustrate our explanation. It will be abstracted to routing engines, line cards, fabric cards, fan trays, and power modules. These field replaceable parts contain a lot of electronic components, and multiple parameters can influence their power usage. Among those parameters, 2 are common to every electronic part in the device: the temperature and the elevation. Indeed, we can break down the power used in 2 parts, the static part and the dynamic part. The static part is also referred as leakage power. It's the current that flows through the transistor when there is no activity. And this leakage power is almost linearly increasing based on the temperature. Take a look at this line card configured with 36 ports 100 GigE on the left and 400 GigE on the right, and they are not doing anything. The power used is regularly increasing when the ambient temperature goes up. Now, the second parameter that influences every single electronic component will be the elevation, and for a simple reason. The cooling capability is a function of the air pressure, and therefore the altitude. We use a simple rule of thumb to say that 1000 feet, around 300 meters, is equivalent to 1 additional degree Celsius at sea level. Consequently, to support a system at 1800 meters of altitude, you need to test it at the maximum temperature plus 6 degrees. In our recent routers, that will be 40 plus 6 equals 46 Celsius. Now, let's see what's on the back of your chassis. The power consumption of a fan is a cubic function of the rotation speed, and this speed is influenced by the hottest point in your chassis. Indeed, we have multiple sensors scattered all over the board, and in the components. The job of the fan is to make sure that every part stays in the operating limits. So we have a mechanism called EM policy, EM for environment monitoring, that smartly adapts the speed of the fans to optimally reduce the temperature in the router. Maybe we can go into the detail of this EM policy one day. Just let me know if you're interested in such a topic. Still staying in the back of the chassis, we also have the power supply module, the PSMs, or PSU for power supply units. These PSMs are both a consumer and a provider of energy. Consumer because they contain a fan. So depending on the sensors, it will operate at a different speed and consume more or less energy. The main job of the PSM is to convert the current provided by the grid, like 222 volt AC or 48 volt DC, into something usable by the router cards and components. Usually it's a 12 volt DC feed, but some systems may need different voltage, like 52 volts. The conversion job is done with an efficiency ratio and some energy is lost in the process. And it's important to note that efficiency is not a fixed number. It depends on the power load of the PSM. By load I mean the percentage of capacity used for a particular module. And we observe that the top conversion efficiency is reached around 40 to 60%. That's why inserting too many PSMs or connecting too many feeds in your router can be detrimental, since it will lower the load on each module and it will decrease the conversion performance, moving you at the left side of this diagram. Also, it's important to know that voltage conversion is done in multiple parts inside the boards. We have POLs, point of load converters, that will convert it to lower voltage current to feed different components. Some part will need 0.8, 1.5, 3.5 volts, etc. Here again we have a conversion efficiency, and that's also valid for the optic modules. And talking about optics, of course their power usage will depend on multiple factors. 100 GeV SR4 will not consume the same amount of energy than 800 GeV ZR. So the speed, type and reach are of course parameters. The question of the influence of the amount of traffic going through the optic is an interesting one. If the module does not do a lot of signal treatment, it will not be a significant parameter. But of course, a coherent optic containing a DSP performing advanced error correction, it will become an important influence on the power usage. It's common to present only the maximum power of a pluggable optic, like 3.5 or 4.5 watts for this QSFP28 LR4. But we observe a lot of differences in the performance and power usage of optics of different brands, and even between different models and generations of the same brand. Note that temperature is also a key factor, and it does not impact all models in a similar manner. One last word on the optics before we move to the next component in a board. It's important to treat high power optics as a specific case. Indeed, they will preheat significantly the airflow entering the router, and we have seen earlier that it has an important impact on the leakage power of all internal components. Consequently, when you measure the power used by a system, you cannot execute a test in your lab with a router just wired with DAC or AOC interfaces, and then add up the power used by your high power optics, like 22 or 25 watts per port. It will not be an accurate estimation, because with low power optics, the internal temperature of the chassis will be much lower, and consequently, the leakage power will be lower. So you will need to execute a very specific case with high power optics to be realistic. Now, let's progress into the description of the internal parts of the line card and the fabric card, and talk about the PHYs. These components are Ethernet transceivers that can be programmed in different modes to deliver different types of services. For example, it can be used as a retimer, and its job then will consist in boosting and realigning the electrical signals circulating into the board. It will help when you have long traces or when you have a connector that creates electromagnetic perturbation. So retimers are needed for signal integrity if you want. And in other configuration, a PHY can be used to create a larger fan out and increase the port density of your routing device. For example, in reverse gearbox mode, we are converting 50 gig SerDes on the PFE side into twice 25 gig SerDes on the interface side. The conversion includes the re-encoding from PAM4 to NRZ and different error correction on each side. What influences the power used by PHYs? It will be traffic first, but also the features we enable on these devices. Indeed, on top of retimer and gearbox, they can handle certain tasks like timing and encryption. In this example, we are comparing the power used on SCX7100 based on traffic when we have MACsec enabled or disabled. And in this router, MACsec is done at the PHY level. So you can see at least 10 watts of difference here. Now, let's talk about the top energy consumers in our routers, the packet forwarding engine. Many factors can be influential here, like the PFE state. Indeed, we can operate the PFE at a different clock frequency in certain cases, or we can put the chipset in a sleeping mode, in reset or power off in certain other cases. Then the power usage will vary depending on the port configuration. If the port is empty, that should have an impact on the state of the SerDes and on the PFE. Same if you configure the port in unused mode. Traffic is of course very important, but we are coming back on that in a minute. Finally, the features could have also an impact. It will be more impactful on the run-to-completion architectures compared to the pipeline ones, but still it may have an influence. We said traffic is a factor of the power usage. With this example of SCX 7100, we can even say that traffic impact is almost linear. From no traffic to line rate on all ports, we can see this progression that represents 95 watts in total. And by the way, do you think it's dependent on the bandwidth, or could it be driven by a different factor, like the number of packets per second, for example? That's what we want to demonstrate with this other experiment. Here, we keep a constant PPS, like 10 million packets per second, and we increment the packet size from non-drop rate to line rate. The result of this test is interesting. If we keep the PPS constant, we notice the power usage difference from NDR to line rate is only 15 watts, much less than the 95 watts we measured in the previous test. And so we can directly conclude that traffic influence on power is more dependent on the number of packets we need to handle per second than the bandwidth in bits per second. And it's a good news, because with video taking a larger part of the internet traffic every year, the average packet size is constantly growing. Let's conclude on the PFE side with one last component, the external buffer. Of course, like every other part, it consumes energy, and that's directly dependent on the amount of traffic it needs to handle to store packets. In this PTX example with Express 4 chipset, we noticed a difference of 15 watts between the situation with no traffic going through the HBM interface and when we have 100% of the bandwidth to the memory being occupied. This aspect must be taken into consideration when we are defining the maximum use case to measure power consumption. Now let's move on to a different component in our routers. Let's talk about the CPU and the companion SODIMM DRAM. We have them in all the routing engines and most of the time in the line cards. The power usage here is dependent on the CPU core activity. It will be solicited by network events triggering routing protocol updates, management activity and streaming telemetry, but also by third-party applications running in containers. As an example, we run a script to stress all the CPU cores of an SCX 7100 during a couple of minutes. We can see a 20 watts difference compared to the idle nominal state. Quite frankly, I'm not sure we want to do much on the CPU side in terms of power usage, simply because we expect all the cores to be optimally used to instantly react to the networking events and to converge as fast as possible. So aside constraining third-party applications to certain limits, probably not much will be done here. And let's conclude this discussion with the Fabric ASIC and the Fabric SerDes. The power usage will be influenced by the traffic, that means the amount of cells they need to switch. And of course, the other factors will be the number of PFEs they need to interconnect. If a chassis slot is empty or if a PFE has been powered off, we want to shut down the SerDes and connection to those elements and not consume energy for no reason. Okay, that answers the question what consumes energy in your routing device. In the next video, we will see what can be done in a concrete manner to optimize this power usage. You will find the link in the description below. See you there.